Welcome to the preparation videos of the course Mathematical Foundations in Software Engineering. This is the fourth video in the series on statistics and probability. We will now continue to talk about special random variables, while later we will dive into the topic of distributions of sampling statistics. In statistics and data analysis, you will start to see that certain random variables occur over and over again. Here we will shortly cover the most common ones and when to use them. This will be a very short introduction, and the idea is that through examples in course literature and through practice during the course, you will get a better understanding on when to use them and how to use them. The first distribution we examine is the Bernoulli distribution, a very simple distribution. Imagine an experiment where the outcome is either success or failure, that is, indicated by the values 1 or 0. Think of it as a coin toss, possibly with an unfair coin, with different probabilities of showing heads and tails. The probability mass function is then given by p x equaling 0 equaling 1 minus p and the probability of x equaling 1 equaling p. The expectation of a Bernoulli random variable is the probability that the random variable equals 1. In RStudio, if you want to have a probability of success that is 0.2, you simply write rbinom, enter 1 to generate one value with size 1, that is a 1 or a 0, and then you enter the probability. Try this on your computer. The next distribution is a logical continuation of the Bernoulli distribution. The Bernoulli distribution was a one-shot thing, while the binomial distribution is a Bernoulli distribution which we run over and over again. It's supposed to simulate an experiment where we run repeated trials that are independent of each other. So, once again, think of it as a coin toss, possibly with an unfair coin, but we do it many times. In RStudio, you simply use the same function, but you ask it to generate maybe 1,000 random variables with a probability of 0.2 of generating a value of 1 or success, as we also might call it. You can also store all those values in a variable, let's say x. Then we can use the table function to get it tabulated. So in this case, remember now that we are talking about random numbers, so the output will be non-deterministic. I got 787 zeros and 213 ones. Of course, we can plot this easily by using the table function's output as input to a bar plot function. And voila! We have a bar plot of the random variables we generated. And as you can see, approximately 20%, i.e. p equaling 0.2, are ones, or success as we might call it. In short, the binomial distribution describes the outcome of n independent trials in an experiment. Each trial is assumed to have only two outcomes, either success or failure. If the probability of a single successful trial is p, then the probability of having n successful outcomes in an experiment of n independent trials is as follows. Now, the ni thingy we have in the formula is simply the number of different groups of I objects that can be chosen from a set of n objects. It is often read as n choose I and called the binomial coefficient. The binomial coefficient can be rewritten to n factorial divided by I factorial times the n minus 1 factorial. In RStudio, we simply write choose 5, 2 in order for us to know how many ways there are to pick 2 items from 5. Here the answer is 10. I would strongly recommend you to calculate this by hand a few times so you get a feeling for how it works in practice. If x is a binomial distributed random variable, n being the total number of experiments and p the probability of each experiment yielding a successful result, then the expected value of x is n times p and the variance is n times p times 1 minus p. Try also to plot various binomial mass functions to see what happens when you change the probability variable. We've now covered two simple examples of special random variables, Bernoulli and binomial. Let us now next look at the Poisson random variable. Some examples of random variables that usually obey the Poisson probability law are the number of people in a community living to 100 years of age, or the number of transistors that fail on their first day of use. In the examples, you will see that we are talking about large amount of data points, where there is a very, very small probability that it has happened. It, in the examples, is the number of people living to 100 years or the number of transistors failing on the first day. The probability mass function of the Poisson distribution is e to the power of minus lambda times lambda to the power of I over I factorial. The symbol e is a constant approximately equal to 2.718. In RStudio, as an exercise, use the function dPois to plot various distributions while changing the parameter lambda. The expected value and variance of a Poisson variable is equal to the lambda parameter. Let's now look at one of the most common distributions of random variables, the normal distribution. A random variable is said to be normally distributed with parameters mu and sigma square, and we write it in the following way. Its density is the following function. The normal density fx gives us a bell-shaped curve that is symmetric about mu and that attains its max value of 1 divided by square root 2 pi sigma, which is approximately equal to 0.399 divided by sigma at x equaling mu. The expectation of x equals mu and the variance equals sigma squared. As an exercise for you, please plot different normal distributions in RStudio.